Okay, my name is Daniel Reznik. I'm with Siemens Technology Group, and I would like to talk a little bit on the industrial perspective, or how industry faces the process simulation in additive manufacturing. And I'm very glad that we had the talk from Michele, which is very in line with what I'm saying. Because there's actually a difference between what academic type and industrial type questions are. I won't say that industrial only work on industrial question, and academic institution can work on industrial questions too, but the academic type question is more of, do we understand the physics? Will this set of process parameters yield sufficient material quality? And typically, what I see as academic type of a questions, you can run it on a small material specimen. Now, if you're in industry, you usually had these things already done. So you've printed your parts or your material specimen, your density cubes, you've done metallurgy, and you had quite an extensive process to get the material released for manufacturing. And the material quality was fine on the test specimen, but the question is it going to be the same in my concrete part? So it's like the famous video, will it blend? It's will it print? You have a complex design, and then you need to simulate it, and you keep the fingers crossing that the part will come out of your printer the way it's supposed to be. So you have to take care for your complete toolpath. And just a note, maybe it's surprising, but most industrial users do not have a supercomputer cluster under their table. They have to do it on a laptop or a workstation. So in this talk, I will present some examples and challenges for complete toolpath simulation for 3 different metal additive manufacturing techniques. That will be the laser powder bed fusion, the wire arc additive manufacturing, and maybe a little bit of exotic, the cold spray additive manufacturing. Maybe for some of you, that's the first time to hear about it, but it's quite interesting also for the simulation challenges and the simulation perspective. So let's start with the laser powder bed fusion. This is what we expect to see, those highly complex, beautiful, shining parts. This is the most common metal AM technique. We rather build small or mid-size components, smaller than 500 millimeter typically, with a very high level of complexity. We've seen the chuck holders from the presentation before, and on each fair you see heat exchangers and other very intricate complex things. Looking on the toolpath structure, we find out that this is in terms of toolpath organization, it is rather simple because it's a 2.5D approach. So you have the slicing, and all the laser movements happen in 2D, and then you go to the next layer and repeat again. So the toolpath is quite simple in organization, but we have low power intake, we have very high spatial resolution, and because the spatial resolution, the thickness of the track and the layer thickness are low, we have extremely long toolpaths. Extremely long, talking about tens of kilometers. And a good measure for complexity for simulation is, I find, to be the toolpath aspect ratio, just dividing the toolpath length by the track width. And here you have something like 10 to the 8th. which has implications for numerical analysis of the whole toolpath. So everything seems to be fine with laser powder bed fusion, but from time to time, there's a problem which is associated with local overheating. As I said, they happen from time to time, but they have the potential to corrupt complete builds by destroying the ricotta. So if you take this typical component out, this could be this kind of impeller, and you look on it on the microscope, you see those kinds of overheated beads at some positions. It's maybe doesn't look nice, but it has a real danger of compromising your quality. And the challenge to track those local overheating is the fact, well, where do they come from? You have adjusted your process parameters on cubic specimen, typically. Now, if you move into more complex parts, you have to introduce some short vectors and less attached mass in going into some level of overhang angle, and that leads to larger melt pools. Now, the complete exposure, you have to capture the complete exposure toolpath to make this analysis. Otherwise, you will not find them. If you're doing, as Michele said, a kind of layer by layer homogenized analysis, you will never find those local effects. They happen somewhere here due to some peculiarity of this specific toolpath. And we need some innovative calculation methods, because you will never get it with direct finite element analysis. It's for this value of toolpath aspect ratio, it doesn't seem to be feasible. Now, what we actually applied in order to track this problem is basically a model order reduction. If you look at this kind of system, we have the melt pool analyzed by conventional finite element analysis on a typical hatching strategy, having this meandering movement back and forth. And then if you inspect a single point, now here annotated with the red or magenta dot, and you look at the temperatures at this point. So you have at some point T0, you have the actual melting, okay? You have some preheating from preceding vectors, and you have some post-heating for subsequent vectors. And looking quite carefully into many of those scenarios, we found out that actually you don't need the whole temperature to capture the whole temperature transient. It could be enough to predict the recurrence temperature, which is the temperature which you have at this point when the laser comes again at the blue cross point. If you're rising this point over melting to some degree, then the two melt pools from the previous and the actual beam will come together and give you, let's say, a grown up of menisc. And this seems to be critical to find out the criticality for the overheating. Now, the solution we developed was to extract a machine learning model which is able not to predict the whole transient, but to predict the recurrence temperature, and to train this model by a series of finite element analysis of representative volume elements. So how the training looks like: you do some finite element calculations, like 500 runs of different lengths, different schedules of vectors, different overhang angles. Extract a machine learning model out of it. It does not necessarily, this pictogram shows you a neural network model. It also works with random forest, for example, and other things. And then we have to look again on experimental parts and experimental specimen and do some fine tuning, some calibration of the model for this specific material. For this specific, there are some fluidic effects here which are not accounted for by the finite element calculation. And once you've done, you have a trained machine learning model. Of course, if you change material or change your parameter set combination, you may need to train your model again. Now, in the application, what you then can do is take the complete build job data, feed it into your machine learning model, and then get the criticality values as calculated here, plus a corrected build job. Now, if you see this fur around the actual build, it's actually a workaround, because what we wanted as a first measure to implement a pause command. But on some machines, some machines do not understand the pause command, so we introduce a vector with a power of 0, which only goes back and forth to mimic a pause. So we introduce those fur to those vectors. The fur is not writing; it's just making the laser go back and forth. It's not a industrial solution, but it works. So once calibrated, this compact model allows a fast evaluation of a complete exposure toolpath. We actually can analyze a complete component within several minutes on a workstation. So the proof is, of course, are we able to correct? So if you compare the original part with the corrected part, we see that we get those overheated indefinite bead out, and we have those definite paths of the welding. Now we applied it to industrial parts. Not all of them would actually, let's say, lead to a process break, but here and there you find those shiny areas where we have an indication that the tracks are kind of welded together and start piling up. And those larger areas have introduced a contact between the part and the recoater, and your process capability is clearly limited. So running our program on this kind of vein structure, we see exactly at those critical areas that the criticality is examined to be high. This is a very efficient calculation. And after the correction, introducing those fur vectors removes all those shiny areas from the part and gives you a clearly enhanced process capability. So as of today, we have a limited amount of trained models for material and process combination. We have a successful test with a aerospace customer, but we have some limitations. And the limitation is the most severe one is that the process assumes a fixed scheme of the meandering exposure vectors, and the new process parameters require model recalibration. Now, we also do not catch some effects like multiple adjacent heat sources, pulsed exposures, etc. So what we are developing now is a similar algorithm based on a more rigorous mathematical approach, modified Green's functions. We hope to develop the possibility to have one model calibration per alloy instead of per process parameter set, and then be able to account for arbitrary energy input, including multiple heat sources and so on. So going over to wire arc additive manufacturing, the parts may look like this. Not so beautiful. Need some post machining typically. This is maybe the most straightforward metal AM technology. You only need an arc welding torch and a robot. You are clearly capable of building much larger scale parts, and as I said, you are near net shape. Now the toolpath structure might be quite complex. If you're using a five-axis CNC or a 6-axis robot, the toolpath structure may be much more non-2D as compared to powder bed fusion. You have more power, so you have to take care, a little bit more care on your overall, your global thermal management, not so much on the local overheating, but on the global thermal. The spatial resolution, as Michele said, is lower. So, and the tool paths are shorter, talking about 100 to 1000 meters. At the end, you are at a toolpath aspect ratio of 10 to the 4th to 10 to the 5th, which enables full path finite element simulation. That will go. So if you look at this kind of a typical fairly complex process, we have for this bracket device a staged toolpath where each stage, the stages are working in XY plane, but they have those loop form transitions from one position to the other. And the loops in Z direction, they show the non-welding movements. We're talking about an overall simulation of physically 5,000 seconds, so 1.5 hours. And actually, the challenge for this simulation is avoid programming of the thermal simulation task. So to use the existing toolpath representation in order to feed the simulator. And connected with this to automatically activate or deactivate elements and the heat sources. So this is quite similar to what Michele told us. The difference is that I'm working here with a standard finite element solver and a standard finite element mesh. In a prototypical implementation, we just designed a small script which translates the G code into a kind of a tabulated XYZ coordinates of the two center points. So you have the G code with feeding instructions, with non-cutting move instructions, and so on. And we just have to translate it to something very simple, like time, X, Y, Z, and a switch variable to distinguish between welding and not welding operation on the next movement. And the element activation and the welding heat source are implemented as marching heat boxes around the tool center point. So if you look then, I hope I'll not go for the video because you probably won't see it, but I can just scroll it through. So this is the activation of the elements happening just over the time. And once the elements are activated, we can go over and just run a thermal simulation. the points which are jumping in this picture are indicating the position of the tool point and the position of a virtual sensor, which is correlated to a real sensor, a parameter sensor working for process monitoring. So in this, we can, using standard finite element tools, you can do in a fair time frame thermal FEM calculation of complete welding tool paths with not too high values of tool path aspect ratio. The last point, cold spray additive manufacturing. Let me first introduce the cold spray process, because it may be not quite well known for some of you. This has been originally developed as a coating technique. So you're operating with metal powders which are accelerated. You have a heater and a high pressure gas. The high pressure gas is heated and mixed together with the powder, and then it's expanded over a Laval nozzle. So the metal powder components are accelerated with the accelerating gas flow and hammered on the substrate. So the layer formation in cold spray is mainly based on forging rather than on melting. And well, it has been introduced as a coating technique, but some people actually use it for additive manufacturing, especially for if the alloy is non-weldable or hard to weld, because you don't weld it, you just forge it together. And it works quite well in some multi-metal or graded material combinations. So here are two examples of rocket nozzles, where the challenge is to combine copper with nickel, which doesn't weld very well together, but you can combine it by this kind of technique. Now, the challenge in cold spray additive manufacturing is the fact that the deposition mainly depends on the normal component of the impact velocity with which you hit your surface. So if you do, for example, as shown here, a repeated passes on the same location, going back and forth as you do it on DED, one would expect to build a wall, but what actually happens is that you build a triangle, because the deposition on the sides of the triangle has lower deposition efficiency as on the flat surface, and then everything will build self-limited to some height, and then the deposition ceases. Also, the shape and the height are dependent on the tilt angle between the nozzle and the substrate, which might be okay for a substrate, but it's getting harder if you build something up and you have to track what you have already built. So the prediction in cold spray additive manufacturing, the challenge is actually the prediction of the shape. Differently from DED welding, where you actually know what element you activate when, here the prediction of the shape of what you deposit is non-trivial and needs to be treated numerically. And what I've done is to apply level set methods to track the deposition boundary. Usually apply level sets in CFD. So you take an auxiliary scalar function between -1 and 1, and the level set phi is equal to 0 is defined to be the moving boundary of the deposition. Impose a level set differential equation of this type with some front velocity, which is calibrated from experiment. And what you can see is if you, for example, program it to be a Gaussian beam on a flat surface. Now those 3 points represent the position of the nozzle or the orientation of the nozzle. And now we go further in time, the nozzle passes around, and when we build something which looks like a Gaussian profile, we could also program it to be triangular. And now the question is, what happens if you tilt the nozzle? Well, you have to calibrate it to your experimental results from here. And if you've done it correctly, then you will have a profile which looks good. So this is like the first step to simulate elementary tracks. But to prove, you need to have some process planning and a known technique to build, for example, vertical walls in cold spray additive manufacturing is to do alternating vertical and tilted passes. So you have pass number 1, which is vertical, and then you tilt to one direction, then you tilt to the other direction, and then you repeat. And if you repeated it several times, then you can find out that you build a wall. And once you can build a wall, you can build components. So this is like the elementary cell of everything. And now with this level set-based techniques, we can do the same on the computer. We don't need to experiment. So this could be the first central track, the left side track, and the right side track. And then we find out that we've built something which looks like a first store. And then we repeat it again in a central track plus left side. Plus the right side. And it seems to work in the way.
Daniel, sorry to interrupt. Let's say, can you finish in 1 minute or a little bit?
Yes, I'm finishing in 1 minute.
Okay,
so the simulation enables us to provide offline process planning for cold spray additive manufacturing. And just then to hurry up, as of today, we know that additive manufacturing techniques are still far from providing first pass right performance for industrial application. Many things might go wrong, especially if the parts are complex. This emphasizes that we need full toolpath type of process simulation. And due to the multi-physics and multi-scale nature of the process, this field will remain challenging for the next years and require a diverse toolbox of modeling approaches. I would like to thank you very much.
Thank you very much, Daniel. Very inspiring presentation. The presentation is open now for questions and discussion. Ernest has a question, please.
Daniel, thank you very much. Really very interesting. I have a question to your first part. So the training phase of the neural network. You said you had about 500 finite element calculations. Were these for one layer, or did you also include several layers above each other for the training?
Yes and no. The answer is actually we provide information about the preceding layers, but this is numerically homogenized. So we start from a quasi-static reference temperature.
Okay.
So it's layer. The solution happens in the layer, but we have information whether this layer operates at 100 or 150 degrees C from a layer by layer solution, as it's common in industry.
Okay, thank you. So thanks a lot.
Okay, there is a question from Adrian Liu. Adrian, please.
Yes, thank you, Daniel. That was a great presentation. You know, mine might be a trivial question, perhaps, but would in the SLM case or the PVF case, you're doing the simulations to prevent the overheating, but in the wire deposition, I did not understand what the goal was. Maybe you can clarify that.
Maybe I didn't express it very much. Actually the goal here is to keep track that the temperature or in here will not be too high for, let's say, the temperature of the area you weld to should not be too high, because then you get the degradation of the material. So it's like keeping the thermal budget or the overall thermal budget of the simulation correct. So if you raise the temperature above some value, then you get problems with oxidation, for example.
Okay, thank you very much. There is also a question from the on the chat. If you can give some details on which tool you use to transfer the G code to the coordinate in the finite element system. Is a trivial step or is an elaborate step, and which tool did you use?
It's quite a trivial step. It's a short Python program, basically. It's not a big thing. You have to consider all those G and F commands in the G code, and you have to translate them into times and coordinates. But it's not. I mean, it's not a great informatic challenge. I think every student can write this translation once he or she understands what is meant by the G code.
Okay, thank you very much.